Hello everyone. Um, in the previous lecture we discussed about Thevenin's theorem. In this lecture we will discuss about a very similar theorem which is called Norton's theorem. So let us start. In the previous lecture when we discussed about Thevenin's theorem, we said that generally the goal is to represent a very difficult circuit which is represented by this linear two-terminal block with just terminals A and B, right? So what we are saying is that inside of this circuit there can be different number of voltage sources, different number of current sources connected with multiple resistors. But what we want to do is we want to represent this complicated circuit using just one active source with a resistor, right? Like in the previous case for Thevenin's theorem, that was a voltage source in series with a resistance. Here in this Norton's theorem, what we are going to do, we are going to represent this same circuit with a current source in parallel with that resistance. So the current source we are using, we are calling that IN or Norton current, and the resistor is called Norton resistance. So this is the thing we have to do. Now how to find out this value of IN and RN, that we will try to learn here. So finding IN, so the same circuit is shown here. This is the linear two-terminal circuit with two terminals A and B. To find the value of IN or Norton current, what we have to do is we have to short these two terminals A and B just like this one. Then some short circuit current will flow inside the circuit, inside this circuit through terminal A to B, right? This short circuit current ISC can be considered as the Norton current for our circuit. So this is kind of equivalent to your Thevenin voltage or VTH from the previous case. Okay, so very simple. Then also we need to find the value of resistance. For this case RN or Norton's resistance, right? Just like your previous case, here we will have two different cases for finding the value of equivalent resistance. One of the cases is when the network doesn't have any dependent sources. All the sources we have inside this circuit is independent sources. So for that case, what we have to do, first of all, we have to turn off or disconnect all the independent sources we have inside the circuit. Then we can find out the equivalent resistance for this whole circuit, which will be called the Norton's resistor. So one thing to remember here is that previously in Thevenin's theorem, we tried to find similar kind of equivalent resistance, which was called Thevenin's resistance. That Thevenin resistance and here this Norton resistance is exactly the same thing. So the two cases we are going to follow here, that will actually be very similar. Okay, so this is the first case. So let us see one example of that. So here we have a circuit where we want to find out the equivalent resistance Rn from this one. So for that, first of all, we have to disconnect all the independent sources. To disconnect the sources, just for the voltage source, what we do is we just try to short circuit removing that voltage source, like for this one. And for the current source, we want to open circuit that portion. Okay, so what will happen here, you see this 32 volt voltage source we have here. Here we just short circuited that portion, and for the current source we got here, we will just open circuit the whole current source. Then we will have a circuit without the independent sources, and then we can find out the value of equivalent resistance for this particular circuit, which is Norton resistance or Rn. So this is for case 1. Before discussing about case 2, which has dependent sources in it, let us first try to solve one example following that case 1. Okay, so we have this example problem 1 here. We will try to solve this one. So this is our circuit. What they are saying is we have to find out the Norton equivalent circuit of this circuit at terminal A and B. So generally what happens is we can have different resistors or different loads connected here. It can happen. So this is the load we want to drive using this circuit we have here. But before calculating the equivalent circuit or Norton equivalent circuit, we have to first of all disconnect this portion. For this example, already this thing is disconnected, so we don't have to worry about that. But after that, two things we have to find out. One of the things is the Norton current, another one is the equivalent resistance, which is called Norton equivalent resistance. Okay, so first of all, let us try to find out the value of equivalent resistance Rn. So here you can see we have two different independent sources. One of them is this current source and this is the voltage source we have. So we have to disconnect them first before calculating the Rn or equivalent resistance of this circuit. So how to do that? We are just going to open circuit this current source and short circuit this voltage source. Then the circuit should look something like this. So we have open circuited this portion, and for this one, I mean in series with this 4 ohm resistor, we have just disconnected 12 volt voltage source and short circuited this particular portion. This is our equivalent circuit, and across A and B, what is the equivalent resistance we get? That will be the value of Rn, right? So if we just try to calculate the value here, what will be the value? So we can just add this one, and this one, as these three resistors are in series. So 8 plus 4 plus 8, this is the amount of resistance we get here. They are in series, right? So total it should be 20 ohm, right? This 20 ohm is again parallel with this one, is in parallel with this one. So 5 ohm in parallel with 20 ohm. So this can be calculated something like this: 20 multiplied by 5 divided by 20 plus 5. This is the total equivalent resistance. So it should be what? 100 divided by 25. So we have Rn equal to 4 ohm, right? This is 4 ohm. Next we have to find out the Norton current. So what we do, this is the initial circuit we have here. First of all, we have to short circuit these two terminals, right? A and B. Then we will get this circuit here. We just have to find out the current flowing through this particular path from A to B, which is the short circuit current ISC. We can also call that IN, the current we want to find. So we first of all have to solve this circuit, then we can get the value of the short circuit current. Now let us try to solve this circuit. First we need to look at this portion. Here you will see we have a short circuited path in series with this 5 ohm resistor. That means no current should flow through this 5 ohm resistor. All the current should flow in this direction. Why is that? To prove that, what we can do is we can take a current here. Let us call that I, and that current is divided into these two current, I1, and this one is actually IN. We can call that IN. So total current I is equal to I1 plus IN. That is what we can write. Now we have to find out what is the value of current I1 and what is the value of current IN. This is just for understanding. We still haven't calculated anything. So to find the value of I1, we can use or apply current division law. So we have two resistors in parallel with each other. So the current for this particular path with 5 ohm resistor should be equal to the resistor for the other path, which is this one, right? This one, which is 0, and the resistor of two paths added together at the denominator. So we can just write that here 0 and 5 multiplied with the total current, which is I. So this is 0 ampere. So 0 ampere current should flow through this 5 ohm resistor. I1 is equal to 0 ampere. And if I want to find the value of IN, that should be IN is equal to the in the numerator should be the value of resistor from the opposite path for this one, right? So at the top, at the numerator, we will have 5 ohm, and at the bottom we will have the summation of 2 resistors. So again 0 plus 5 multiplied with the whole current I. So 5 and 5 should be removed, so we have I. So through this path we will have total current I flowing, right? So that means we can actually omit this portion because this is not contributing to anything. No current is flowing through this particular path. This can be considered as an open circuit, so we can just remove that. So we will just remove this portion because all the currents are flowing in this direction. Now we should try to solve this one. What we can do is we can use nodal analysis. For that, how many nodes we have? Let us call this one the reference node. We will take this one as the ground one. This is the 0 volt reference. Then after that we have this particular node here, this particular node here again, and let us not take any nodes here. We can just consider these two resistors in series with each other, so that will be 16 ohm, right? So only thing we have here is this node here. Let us call that Vx. This is Vx. And then what we can do is we can calculate the amount of current flowing in and out through this node. So 2 ampere current is going in. We should give a current direction for this one, and let us call that what? Maybe Ix. And also some current is flowing in this direction, which is actually In, right? This is In, the current going in this direction. Now let us use Kirchhoff's current law. So 2 ampere current is going in this direction, right? And that is divided into these two portions. One of them is this Ix, another one is this one, which is In. So we can just write Ix plus In. Yeah. What is the value of Ix? Ix can be represented as, you know, the higher voltage minus the lower voltage divided by the resistance, as we have learned earlier. So we can just write in the numerator we will have Vx minus the lower voltage 12 volt divided by this resistor 4 ohm, right? And for In we can just write again the higher voltage is Vx, so current is flowing in this direction, right, like this, and finally going through this reference node. So we can just write Vx minus the reference node, which is 0, divided by the total resistor. So here we have this 8 ohm resistor added with this 8 ohm resistor, so in total 16 ohm resistor. So this is the whole thing, right? We can again equate it here. Now we have to find out the value of Vx, right? So let us try to find out the value of Vx. We can multiply both sides with 16, so that will be 32, and here it should be something like this. Four plus Vx, right? And then we can again simplify it further. So 4 Vx minus 48 plus Vx, we can keep this here, So it will be 32 plus 48, and here we have 5Vx. So this is 80, right? And this is 5Vx. So Vx is equal to 16. So we have found out the value of Vx, but we need the value of In, right? To find out the value of In, we can just take this portion, right? Because this is equal to In. So it should be Vx divided by 16. So Vx is already 16. That means In should be 1 ampere, right? So we have found out the value of In, which is 1 ampere, and previously we also found out the value of equivalent resistance here, I think, which was 4 ohm. So now we can actually form the equivalent circuit, Norton equivalent circuit, from this calculation. So that should be looking something like this. So this is the current In, or Norton current, and in parallel we have this equivalent resistance, which is Rn. So this whole circuit, this total circuit, is represented by just one current source in parallel with a resistor. Now let us look at case 2. Here, so for finding Norton resistance, or Rn, we have case 2 where we have dependent sources in the circuit. So if we have dependent sources in the circuit with the other independent sources, we cannot exactly remove the dependent sources just like we did for independent sources for calculating the value of Rn. So what can we do for those cases? For those cases, first of all, we can remove the independent sources just like before, but for the dependent sources we have to keep them as they are. Then what we have to do is we have to deliberately connect a voltage source or a current source to measure the value of equivalent resistance Rn. So let me further explain that. So this was the circuit we had earlier, right? This thing deliberately added right now. Okay, so in this circuit we had different sources, some independent sources and some dependent sources inside this terminal A and B. Okay, to calculate the value of Rn, first of all we have to remove the independent sources. That we can do, but for the dependent sources we have to keep them as they are. Then we are going to add a voltage source deliberately here, and then finally solve the circuit to get the value of current going through in this path, okay, which is called I0. So we have added a voltage source V0 with the circuit, and then after solving the circuit we will get a value of I0. Okay, or another way is we can also connect a current source here instead of the voltage source we had here. Then what we have to do, we have to find out the voltage we get across these two terminals. Okay, so that is called V0 here. So we have, for one of the cases we will give current source, find the value of voltage, and for other case we will give voltage sources, find the value of current flowing through that circuit. Then the equivalent resistance Rn should be equal to V0 divided by I0 for both of the cases. For both of the cases, one of the values we will provide, another values we have to find. Then one divided by the other is the value of Norton resistance. Now here for this value of V0 or the value of I0, we have to give some value so that we get a finite value for this I0, right? Generally what we do, conventional value is V0 is equal to 1 volt, which is very easy to solve. Same goes for the current. If we use the current method, then we have to give, I mean not we don't have to give, but we can give 1 ampere, which will further simplify our circuit analysis. Okay, so let us try to see one example based on this case 2. So here example problem 2. In this circuit you can see that we have an independent source here, also we have a dependent source here. That will cause the problem, right? So try to solve this problem. So first of all, let us try to find out the equivalent resistance, I mean Rn. So we will follow the procedure we just discussed earlier. So we have this independent source here, we can remove that, no problem. So this will be just short circuited, right? But for the dependent source we have here, we cannot do anything here, it should be kept as it is. Then we will try to find out the equivalent resistance, right? So that is the equivalent circuit we have here. This thing is short circuited in here. Then another thing is, again, we can think of these two parallel paths here. This path is having a resistor, but this one is short circuited. That means all the current should flow in this path instead of this one, as they are in parallel with each other. But before that we have to calculate the value of Ix, because this dependent source is dependent upon this current Ix. So easily we can say that the value of Ix should be equal to 0, as we had earlier discussed, right? So we have a path here, and this path is in parallel with the previous path. This path is short circuited, but we have a finite resistance here. As a result, what will happen? All the currents should flow in this path instead of this one. No current should flow in this path. So Ix should be equal to 0. If Ix is equal to 0, we can also say the current source, for the current source here, the dependent current source, the amount of current flowing through this one is 0, again for this case, right? If this is the situation, now we can start solving our problem. So now we will modify the circuit as we have described. So here you see we have omitted the 5 ohm resistor, as no current is flowing in this path, and also we have found out the value of Ix, which is 0. So 2Ix should also be equal to 0. If this is the situation, then we can deliberately add a voltage source across the terminal A and B, and let us call that V0, and we will give that a value of 1 volt. Okay, now we have to find out the value of current I0 because of this voltage source. So let us try to use nodal analysis. We will take this one as the reference node, okay, and we will try to find out the node voltage for this one, and we can say the node voltage for this one is V0, because V0 is directly connected with this node and the reference node here. So this node can be called V0. Now if we try to apply Kirchhoff's current law for this node V0, we have this current flowing in the node, and also this current flowing in, which is I0, right? Both of the currents are flowing in the node V0, and we can say, just assume that some current is flowing out. Let us call that what? Let us call that IY. This current is flowing through this path. So we can just write 2Ix plus I0 equals to V0 divided by 5. This is the current flowing through this one, right? So V0 divided by 5. This is the KCL equation at node A, right? Then also another thing is, we know the value of Ix is equal to 0. So 2Ix is also equal to 0. We can just omit that. So I0 is equal to V0 divided by 5. The value of V0 is 1 volt. So we can just say I0 is equal to 0.2 ampere, right? And we had given the value of voltage V0 as 1 volt previously. Here we have found out the value of I naught is equal to 0.2 ampere. So Rn on Norton resistance should be V naught divided by I naught. That should be equal to 1 divided by 0.2 equals to 5 ohm. So we have found out the value of Rn. Now let us try to find out the value of In. So again we have the initial circuit here, this one, the initial circuit, and we have to short the terminals A and B, find out the current going through that path. Okay, so this is the circuit we have to solve here, find out the value of In, then we can represent the equivalent Norton circuit for this initial circuit. So let us try to solve this circuit here. So this one is a bit tricky to solve. First of all, let us think about these two nodes we have here. So between these two nodes we have this voltage source and this resistor in parallel with each other. So we can say across these terminals of this resistor, the total voltage we get is 10 volt, because we have 10 volt in parallel with this one, and this is the positive polarity, this is the negative polarity. So for these 4 ohm resistors, if I want to find out the value of current Ix, that should be the voltage we are getting across the two terminals for this resistor, which is 10 volt, right? And the value of resistor. Then we can get the value of current, right, which is 2.5 ampere. You see, no other portions of the circuit should affect this particular portion here, because we are getting the exact voltage drop across the resistors. As a result, we can use this particular simplification, right? So we know the value of Ix. We can also say what should be the value of 2Ix. It should be 2 multiplied with the value of Ix. So 5 ampere, right? Now let us concentrate on this particular node here. In this particular node, let us call that VA. So in this particular node, some currents are flowing in, some currents are flowing out. So this current is obviously flowing in, and this current IN is flowing out. Let us also assume that for this path, current is flowing in the direction of our VA. And we know for this node, the voltage value is 10 volt if we consider this one as the reference node. So from reference node up to this one, the voltage difference is 10 volt. So we can say this particular node has 10 volt, right? And the current flowing through this one, this current, let us call that IA. That IA can be represented as 10 minus 0. Why 10 minus 0? Because this node VA and the reference node are shorted together, right? So we can say VA is equal to 0. At the denominator we have the value of resistor, so that will be the value of IA, current flowing in the direction of VA. So that should be 2 ampere. And now we can apply KCL for this node, node A. At node A, we will have 2Ix current flowing in plus this IA current flowing in. The current going out is IN. We know the value of 2Ix, which is this one. So let us write that 5 ampere. We just found out the value of IA, which is 2 ampere. And finally we have this IN. So IN should be equal to 7 ampere. So we have the value of IN And previously we also found out the value of resistor, which was 5 ohm, right? So let us also write that Rn is equal to 5 ohm. So we can just represent the whole circuit something like this. So we will have a current source something like this. In is equal to 7 ampere, and which is in parallel with this resistor. Rn equals to 5 ohm, and these are the two terminals A, and this one is B. This is the equivalent circuit we will get finally. Now we are going to learn another concept, which is maximum power transfer. So for this particular concept, what we want to do is we want to get the maximum power for our load. Like let us look at this example here. For this circuit, again we have this linear two terminal circuit here. We can have different number of voltage sources, current sources and resistors interconnected with each other for this linear two terminal circuit. But this is the load which we can control. This is the household appliances we use, like let's say fan or light, and we want to optimize this load, I mean the resistance of this load, so that we can get the maximum amount of power transferred to this load. So we cannot change anything in this circuit, this linear two terminal circuit, but what we can do, we have the option to optimize the value of this resistance RL, and we have to change this value so that we get the maximum amount of power across these two terminals for this particular load, right? Here also what we are going to do is we are going to represent the black box we have here, this linear two terminal circuit, with a Thevenin or Norton equivalent circuit. So there will be one source with a resistor, something like this. So here we have represented the whole circuit using a Thevenin voltage and a Thevenin resistance in series with that voltage. Now we want to find the value of RL so that we get the maximum amount of power across these two terminals. So how to actually optimize the value of RL so that we get the maximum power transferred to this load? To do that, let us try to analyze this circuit. So here you see this simple representation of this circuit, Thevenin equivalent circuit. Now the only thing we can change in this circuit is RL or the load resistance. All other things like the Thevenin resistance here and the Thevenin voltage here, these are internal parameters of the circuit, so we cannot change that, like our household appliances which we run using the outlets, right, two terminal outlets, and we cannot change anything inside of that two terminal, right? What is the voltage coming, what is the internal resistance, everything is fixed. So what we can change is our load, and we have to change so that we get the maximum amount of power delivered to our load RL. So let us try to find out what will be the value of power delivered to this load RL. So let us call that P. P is equal to the current going through this resistor I, so this one I square multiplied with the resistance RL. We can again represent this current with voltage and resistance, that means Thevenin voltage and Thevenin resistance. So that should look something like this. This current I can be represented something like this. I should be equal to the total voltage supplied VTH divided by the total resistance of the circuit, which is RTH plus RL, right? So we can replace the value of I here. So finally we will get that the value of P is equal to VTH divided by RTH plus RL whole square multiplied with the resistance RL. Now this is the amount of power we will get to our load RL, and only parameter we can change here is RL. Now this function, the relationship between this power and this resistance RL, this can be represented something like this with this graph here. In the horizontal axis we have this variable resistor RL, and in the vertical axis we will plot the value of power. And we will see that this curve here, this will start from a very low value, the power will be very low, then after increasing the value of RL, at certain point we will get the maximum value of power delivered to our load. Then again, after increasing the value of RL, we will see that gradually the power delivered is getting decreased. So what is the exact value of RL when we will get Pmax or maximum power? How can we find that out? So if you remember from your intermediate level, to get the maximum peak of a curve like this, we used to use derivatives, right? So if I just take the derivative of this particular curve, we will see that for each of the points we will get the tangent, right, or the slope. And we can see that the slope is gradually increasing in this direction. Then finally, when we have the maximum power delivered, at this point the slope of this curve is 0. So if we can just take the derivative of this particular equation with respect to RL, because this particular curve is represented by this equation, right? So we can just take the derivative of this P with respect to RL. That will give us the value of maximum power if we just equate that to 0. So how to do that? Let us try to do that. So again, let us write the equation. P is equal to VTH divided by RTH plus RL whole square multiplied with RL. So we will take the derivative of P with respect to RL, so that will be this, right, dP by dRL. And here we can write now. Here you will see that this value VTH is actually constant with respect to the whole thing. We can keep that outside, right? So we can just keep that outside. That will be VTH whole square, and this is the thing we have to take the derivative of, right, without that VTH. So let us try to do that. So that will be looking something like this. So RL divided by RTH plus RL whole square, right? So this particular derivative is taking the form of U divided by V. So how to solve that? So if we have derivative of U divided by V, we had to do something like this. First of all, we took V multiplied with the derivative of U minus U derivative of V, and at the denominator we will have V square. So this thing, this particular formula we have to apply for our case, right? So let us try to do that. So here U is actually RL and V is equal to RTH plus RL whole square. So what should be the value of du divided by drl? That should be equal to 1, right? And derivative of V should be equal to the derivative of this one, so 2 RTH plus RL. Then again we have to take the derivative of this one, which is nothing but 1, right? So this is the derivative of V with respect to RL. So we have these two things. We will just put the values in our final derivative here. So let us try to do that. So that should be VTH, and at the numerator we will have V, which is RTH plus RL square, derivative of U, which is 1, minus U, that means RL, and multiplied with derivative of V, so the bottom one. So that should be 2 multiplied with RTH plus RL, as we have just calculated, right? And at the bottom we should have V square, that means the square of this one. That should be RTH plus RL to the power 4. So this is the final thing we get after this derivation. Now we have to equate the whole thing to 0 so that we can get the peak here, because at the peak the slope is 0. So if we do that, basically you will see that we can just say that VTH square is equal to 0, or this portion, this whole portion is equal to 0. So we will take this portion is equal to 0. That means we can just directly say that this particular portion here, this is equal to 0, right? We can just write this portion here, RTH plus RL whole square minus 2 RL RTH plus RL divided by RTH plus RL to the power 4 is equal to 0. We can take RTH plus RL common at the numerator, then we can further simplify this one, right? So it should be something like this, RTH plus RL, then in bracket we will have RTH plus RL minus 2 RL, right? And at the bottom we have RTH plus RL to the power 4 is equal to 0. So we can further simplify these two. So then we will get RTH minus RL divided by RTH plus RL to the power 3, which is equal to 0. So we can just finally say that RTH minus RL is equal to 0, or RTH is equal to RL. This is the final verdict we get here. So that means if RL is equal to RTH or equal to Thevenin resistance, then we will get the maximum power transfer. So this point here, this should be RTH, right? So we have found out the requirement for maximum power transfer, which is RL should be equal to RTH. Now if we plug this value onto our equation of power delivered to this resistor RL, that will be something like this. So P was equal to VTH divided by RTH plus RL whole square multiplied with RL. So here in place of RL we are going to plug the value of RTH. So that should be something like this: P is equal to VTH divided by RTH plus RTH whole square multiplied with again RTH. So we have VTH square, at the bottom it should be 4 RTH square multiplied with again RTH. So the final power should be, the power which is maximum. So here also we have to write maximum, because when we replace the value of RL with RTH we are getting the maximum power. So P max is equal to VTH square divided by 4 RTH. So this is the final one. Now based on these results we have got, we have to solve one problem. So let us see that. So in this problem they are saying that find the value of RL for maximum power transfer in the circuit of this figure, and then also find the maximum power. Before doing that we have to represent this circuit, this one, using a Thevenin equivalent circuit, right? So we know how to calculate Thevenin equivalent circuit. Let us try to solve this one. So first of all, let us try to find out the Thevenin equivalent resistance. So circuit should be something like this. We will have this 6 ohm resistor, then this 12 volt voltage source is short circuited. We will have this 12 ohm intact. This is 6 ohm. This is 3 ohm. And this particular current source should be open circuited, right? So we can just omit this portion. Then we have another resistor which is 2 ohm. This one is 3 ohm. And this is terminal B, this is terminal A. Now we can find out the value of Thevenin resistance here, which is actually 3 plus 2 because of these two, and that portion is in series with this particular portion here, and here these two resistance are in parallel with each other, so we can just write 6 parallel with 12, right? So this is 5 plus if this is parallel, that means we can calculate the value something like this, which is equal to 5 plus 72 divided by, here it is 18. So 5 plus 4, 9 ohm is the equivalent resistance. So we have found out the value of RTH is equal to 9 ohm. Now let us try to find out the value of VTH. So we have to solve this circuit after disconnecting this portion, right? So that circuit should look something like this. So this is the value of VTH. Here we will apply nodal analysis. We have different nodes here. Particularly, let us take this one as the reference node. Let us call this node as Vx. We already know the value of this one, which is 12 volt. Because of this, and this node can be called VTH, right? So if I want to apply KCL in this node, then we can write, first of all let us define the direction of current. For this one, the current direction is in this direction. Let us take current direction for this one as downwards, and for this one we can take this direction. Okay, so that means the current here 2 ampere should be equal to the summation of these two current, right? So this current in this direction, this is Vx divided by 12, and this current here, this current is Vx minus 12 according to our direction of current, Vx minus 12 divided by the resistance 6. From this we can find the value of Vx, right? So let us multiply both side with 12, so 24, this is Vx, and this should be 2 Vx minus 24. So we have 48 is equal to 3 Vx, or we can say Vx is equal to 16. Now from this one we can find the value of VTH. So just look at this particular portion here, right? Here the current which is flowing can be calculated as something like this, right? The current direction is in this direction, so we can say VTH minus Vx divided by 3, right, is equal to the current flowing. We know the current flowing in this direction is 2 ampere because this portion is open circuited, no current is flowing there, so all the currents are going in this direction, right? So 2 ampere, and we already know the value of Vx. We can just place that here, so minus 16 divided by 3 equals to 2, or we can say VTH is equal to 6 plus 16, which is equal to 22 volt. So VTH is equal to 22 volt, and previously we saw that RTH is equal to 9 ohm. Now we can represent the whole circuit using Thevenin equivalent circuit. So we will have a voltage source something like this in series with the resistor. The value is 9 ohm here, and this should be 22 volt, and these are the two nodes A and B, and here we have the variable load RL connected, just like this one, right? And as we have found out the value of RTH is equal to 9 ohm, we can say that RL should also be equal to 9 ohm, because for maximum power to be transferred to our load, the value of resistance should be equal to the Thevenin resistance. So we can say RL should be equal to 9 ohm, and if that happens, what should be the amount of power delivered, amount of maximum power delivered to this resistor? That should be equal to P is equal to VTH square divided by 4 RTH, as we had earlier discussed. So the value of VTH is equal to 22 whole square, and 4 RTH is equal to 9. So that should be equal to 13.44 watt. You can calculate that yourself. So in this way you can actually find the value of RL for maximum power transfer, and then you can also find the value of power delivered, the maximum power to that load. That's all for this lecture. Thank you.